referring to? Rate of change, right? I want to know how fast. What's the rate of change, right? How quickly is it changing? So what am I going to do? I'm going to take a derivative of this, aren't I? Okay. Now, notice something about this. And I'm going to start utilizing notation really purposefully here. The function's a v function. What's the variable within the v function? The r, right? The r is the thing that's going to produce the volume, correct? So what I'm going to say is this. dv over dr. The same way I would say dy over dx if I had a function of y in terms of x, right? Here I have a function of v in terms of r, okay? So what would be the derivative of this function? Well, this is an r cubed, right? Everything else is a constant, right? So it's just a power rule. So it's just going to be 3 times 4/3 pi. What happens to 3 times 4/3? It just becomes 4, right? So this becomes 4 pi r squared, right? And what do I want to do? I want to actually evaluate this now. So I'm going to show you guys a new way to write this, okay? I want to know what is dv dr when, that's like a vertical line, okay? When the radius equals 3. Well, it's going to be 4 pi times 3 squared, or 36 pi, right? Give me a unit here, guys. What am I actually analyzing? I'm analyzing volume, right? So what's the unit? Feet cubed per what? What's the input value? Per radius, yeah. So at that moment, guys, at that moment, that's what I'm actually, that's how fast the volume of the sphere is changing, right? Questions there? Okay. How fast is the surface area changing? Okay, how fast? Oh, by the way, I actually should say what here, guys. Is this an increasing or a decreasing value? It's a decreasing value. It's decreasing by this amount, right? So I would actually use the word decreasing at a rate of blank, 36 pi feet cubed per radius. All right, how fast is surface area changing? Well, surface area is 4 pi r squared. And so my derivative of surface area with respect to the radius is what? What's my derivative here? 8 pi r, right? All right, and I want to know what is the value for how quickly my surface area is changing when the radius equals 3. Twenty-four pi, right? And with a unit, what's that going to be? Square feet per radius. And again, what's it doing? It is decreasing at a rate of 24 pi feet squared per radius. This is kind of a cute little question here. How fast is the diameter of the sphere changing? How fast is the diameter of the sphere changing? Well, guys, what's the only thing we know? We know that a diameter equals 2 r's, right? Yeah, so this wants to know how fast is the diameter of the sphere changing. All right, well, dd dr, the derivative of the diameter, right? What's the derivative of 2r? 2. And what's it doing? At that moment, it's decreasing at a rate of 2 feet per radius. 2 feet per hour. Cool? All right. Really, I'm using that phrase, how fast, right? Talking about a rate, okay? Guys, on that next page, what you have is you have a whole bunch of rules, okay? And over the next day and a half or so, we're going to talk about all of these. And I think the majority of these are intuitive, okay? They just make sense, I hope, as we go through them, okay? Because you've seen all these phrases used. There's not really there that's all that new. But we'll go through it all. Okay, here's what you got. Ready? I have a particle sitting right here, okay? What that particle is going to do is it's going to move along a horizontal line. So what can the particle do? It can move left or it can move right or it could stay in place, okay? We're going to analyze how that particle moves, okay? That's our task. Now what I do in this case is I give you a function for how the particle moves in terms of t, where t represents time, and the particle moves measured in feet. Okay, so I got units, all right? Units are important here. We know that that's our time value and that's our function that represents our movement. And we have units measured in feet and in seconds. All important, right? And it's happening on a horizontal line. So when I discuss and when we write things down in terms of our explanations, that's important to use. Okay? So question A, find the displacement of the particle. This is a physics question for those of you that are taking physics, right? What is displacement? Displacement is where I ended up minus where I started, right? So it's ending minus starting. End minus start. So what does this question ask? It says find the displacement during the first 3 seconds, right? So for this particular case, my displacement is going to be what? It's going to be my, oh, by the way, x of t is what kind of a function? Position function. Yeah, let's write that down, right? This is our position. It's where I am, right? So I want to know what happens in the first 3 seconds, right? So I want to know what happens at the end of the 3 seconds minus the beginning. So what is x of 3? It's 3 squared minus 4 times 3 plus 3. I think that's going to give me 0. Do I really need to plug anything in to get the value for x of 0? No, isn't it just the constant? It's just 3, right? All right, so for this case, our displacement's going to be 0 minus 3. Okay, so let's talk about what happened. Again, I want to be really, really particular about what's happening. So if you were to think about my pen being that particle, right? What did I say the particle is going to do? It's going to move left or right, or it's going to stay still, right? So if I was to ask you to describe what we just did, what would you say? What would you say? What did the particle do? It definitely moved, right? Moved where? Left, how much? 3 units, right? How long did it take? 3 seconds, right? So again, if I'm asking you to explain what's happening, let's be really, really, really specific, right? So what I would say is, from t being an element of 0 to 1, oh, I'm sorry, not 0 to 1, 0 to 3, right? During the first, in other words, during the first 3 seconds, right? The particle moves. Three feet left. Cool, right? Particle moved 3 units left. 3 feet left, actually, in this case. Okay, next phrase. Find the average velocity. Guys, as soon as you see that phrase, average velocity. Is that a derivative? Ooh, it is? Why is it not? What word? What word makes it not? Average. Yeah. As soon as you see this phrase right here, this is just going to be a regular slope, right? This is nothing more than a regular slope. Not a derivative, right? Because I want to know the average velocity during the what? During the first 3 seconds, right? Yeah, so that immediately tells me it can't be a derivative, because what does a derivative do? Gives me a velocity at a moment, at a time, right? At one time, not over the course of 3 seconds, right? That wouldn't work, okay? So find the average velocity. So average velocity is going to equal the change in position over the change in time. So my change in position would be x3 minus x0 over 3 seconds, right? It took 3 seconds for that to happen. -3 over 3 gives me -1, right? So now let's use a good phrase. What am I going to say? What did I, oh, let's put a unit on this first. Feet per second, right? -1 feet per second. Give me a phrase. Give me a phrase. We got to be able to articulate what we're doing, not just do it. I know we can do that, but let's talk about what we actually accomplished. Say again? Displacement over time. Good. I mean, but talk to me like a human being. Don't talk to me like a student. What is the particle doing? What did we just figure out? It's an average velocity, but what does that mean? You're trying to get cute again. Let's not be cute. Don't use the word. First of all, you said down. You said backwards. What does backwards mean? Well, yeah, but I'm on a horizontal line. I mean, let's use the right word. Okay, so the particle is moving left at an average rate of 1 foot per second, right? I mean, that's what's happening, right? It's moving left at an average rate of 1 foot per second for the first 3 seconds, right? So we got to be able to articulate that really, really specifically, right? What am I doing? Where am I going? Unit-wise, right? So the particle, actually, let's say from the particle moves left at, and I got to use that word average, right? Because it could be going a little faster, it could be going a little slower. I just know that over that 3 second period, that's the average rate of change, right? At a rate of 1 foot per second. Good? All right. Find the particle's initial velocity and its velocity at 3 seconds. Okay, hang on a minute. I asked you for velocity at a point, spot, position. So what am I talking about now? Now I'm talking derivative, right? So I want to know initial velocity and velocity at t equals 3. That is velocity at a point. Which means derivative. All right, so let's take our derivative. Our derivative is going to be the same as velocity. What's the derivative of this function? 2t minus 4. All right, so what do I want to know? I want to know 2 things. I want to know the velocity at the beginning and at the 3 second period, right? So at the beginning, I get -4. At 3, I get 2, right? How did I get those? I just took these values and plugged it into this, right? Give me units. Feet per second. Feet per second. Explain its meaning. Okay, so now, guys, now we have to be, again, particular about what's happening, right? So what am I going to actually say? Go ahead. Add 0 seconds. Yep. Exactly, right? I mean, it is moving left at a rate of 4 feet per second. I mean, yeah, so we're being specific about the fact that it's happening at an instant, right? At an instant. So at t equals 0, the particle is moving left at a rate of 4 feet per second. And then what's happening at 3 seconds? At 3 seconds, the particle is moving right at a rate of 2 feet per second. Everybody okay with that? Right? So those of you that are taking physics have a little bit of an advantage right now because, yeah, I mean, this terminology, these phrases sound familiar, right? Find the acceleration of the particle. Okay, what did we say acceleration is? Acceleration is an analysis of the change in velocity, right? So acceleration is the same as an analysis of the change in velocity, which is derivative of the velocity. Well, if I take a derivative of velocity, then I've taken a second derivative of position. What's the derivative of 2t minus 4? Just 2, right? Give me a unit. Feet per second squared. Why squared? Because I've taken a derivative of a derivative, right? Okay, so a lot of people don't like that. Exactly, right? It's how quickly velocity changes, right? So if velocity is feet per second, then I have to analyze the change in that, and analyzing the change in that is talking about feet per second, right? And I want to know what happens at what? 3 seconds, right? Okay. Well, do I need to plug anything in? No. What? Nothing to plug in, right? Acceleration is what? Constant. Okay. So at t equals 3. The particle is, okay, what's happening here? Give me, what are we analyzing again? When we do acceleration, we're analyzing the change in the what? The change in the velocity, right? So how is the velocity changing? Give me a word. I want a word about the velocity. The velocity is doing what? Yeah, somebody said it. Somebody just said it. No, you said it before. Somebody said increasing. Who said increasing? Somebody said it. Yeah, guys. If the acceleration is positive, that means I'm what? Increasing velocity, right? Increasing velocity. Okay. So at t equals 3, the particle is increasing its velocity at a rate of 2 feet per second per second. Right? Increasing the velocity. You could, yeah. Yep. Either way. All right, guys, this one right here, star this one. This one right here is super important. All right, shows up all the time. Very, very important. I'm going to give you a little demonstration, okay? I'm on a horizontal line, okay? I'm moving this way. Velocity is what? Negative. I'm moving this way. Velocity is what? Positive. Okay. So, if my velocity is negative, I'm moving left, right? Now, if my acceleration is negative, what's happening? If my acceleration is negative, and I'm moving this way, what's happening? I'm being pushed this way faster, right? So I'm going to what? I'm going to speed up, aren't I? Okay? So, if my velocity is moving in this direction, and my acceleration is going this way, I'm being pushed this way, right? So I'm going to slow down. Very good. Okay? If my velocity is moving this way, I'm going to the right. If my acceleration is positive, I'm being pushed this way, so I'm going to speed up. If my velocity is going this way and my acceleration is negative, what's happening? Slowing down. So if I analyze that, what can I say? If my velocity and acceleration are either both negative or both positive, I'm speeding up, right? Because if I'm moving that way and accelerating that way, I have to be going faster. If I'm moving this way and accelerating this way, I have to be going faster, right? If I'm moving this way and accelerating that way, slowing down, and then vice versa, okay? So I would create a little chart here, guys, and what I would do is this. I would say we're going to analyze V and A, and we have 4 scenarios, right? I can have a positive and a positive, which means I am increasing speed. I can have a negative and a negative, which means I'm going to increase. I can have a positive and a negative, or a negative and a positive. In both cases, I'm going to decrease. Here's the one that actually don't want to do that. No, hold off on that. Okay. It's almost lunchtime. Exactly. So here's what I got. At 3 seconds, right? At 3 seconds, what was my velocity at 3 seconds? Well, let's go up here. Velocity at 3 seconds is 2. What's the acceleration at 3 seconds? 2, right? So both of those values are greater than 0, right? So what can I say? Am I speeding up or slowing down? Yeah, so since V of t is greater than 0 and A of t is greater than 0 when t equals 3, the particle is speeding up. Right, and that's your justification, right? When the V is greater than 0 and the A is greater than 0, I got to be speeding up at that particular time. All right, justify, that's it, right? During which times is the particle moving to the right or to the left? Okay, moving right, moving left. If I'm moving right, I just demoed that, right? If I'm moving to the right, what's happening? I have a velocity which is what? I have a positive velocity. If I'm moving to the left, I have a negative velocity. And if I am what? If I am at rest, then I have a velocity which is 0. Correct? Do I have a velocity curve? Do I have something that I could actually, all right, we'll do this when we come back. All right, so before we were so rudely before we were so rudely interrupted by the lunch, I know. We got ourselves to this point, right? And what we said was that the velocity was this function 2t minus 4. And I asked you guys, could you graph that if I asked you to graph it? I hope you could give me an idea what it looks like. It's definitely going to be 1, 2, 3, 4, 1, 2. It's definitely going to be a line. Y-intercept at -4. Slope of 2. And I guess I misspoke because it's really not a line, it's really a ray, correct? Because we are only graphing it for values of t greater than or equal to 0. So here's my function for velocity. Well, what's nice about doing this is it gives me a really what? Visual of what's going on. Anywhere this function is below the x-axis, the velocity is what? Negative. So where is it moving? To the left. Yeah, so down here, right? This would be where it's moving left. Okay, the root of this, the root of this is where it's going to be at rest. And wherever this is above the x-axis is where it's going to be moving where? To the right. Okay, so where am I moving to the right? I'm moving to the right from the root on, correct? Do I include the root? No, because at the actual root, I'm equal to what value? 0, so that's where I would be at rest, right? So I would say 2 to infinity is when we're moving right. I am moving left. Now notice, I want to be careful about the way I say this. Moving left is when velocity is negative, right? Was the velocity negative at the beginning, at the 0? It was, right? So I'm going to include that 0 and go to 2, right? Now that's it's sort of, this is where physics and the mathematics sort of, I don't know, maybe like take two different roads, right? Can something go from 0 velocity to a instantaneous -4 velocity? It can, like in physics, can you go from standing still instantaneously to going to -4? I mean, no, right? I mean, there's got to be something in the middle of that. So, I mean, this is not a real life scenario in that sense, right? And then again, what am I going to say? I'm at rest at t equals 2, right? Find the total distance the particle travels during the first 3 seconds. Okay, so what do we know? Well, from 0 to 2, I'm going which way? To the left. And then from 2 to infinity, I'm going to the right. So if I was to sort of show you this, guys, isn't this what I'm doing? Here's my particle. Left, right. Fair to say? So if I want to know the total distance traveled, what do I need to know? How far is it from where I began to the point where I had to turn and go back this way, correct? So really, guys, if I have a velocity of 0, what can I know about that? What does that sort of represent? Yeah, the point where I changed what? Changed direction, right? So to change direction, guys, you're going to want to star this, highlight this. Change direction, 2 things have to be true. Not just one. 2 things have to be true. The first thing, the velocity has to be 0. In other words, I have to come to rest. The second thing that's true is that I have to go from a positive to a negative or a negative to positive velocity. That's the thing that people get sort of a little bit confused by. So let me give you a visual, right? Here's velocity right now is what? Negative. Velocity right now is what? 0. Velocity right now is what? Positive. Did I change direction? Yes. Okay. Watch this. Ready? Velocity is what? Negative. Velocity is what? 0. Velocity is what? Did I change direction? No. Right? So again, I have to go from a positive to a negative with a 0 in the middle. Okay. Otherwise, what I do? I went left, I rested, and then I continued going left, or I went right and I rested and I continued going right. See the difference? Michael.
Um, so of course it has to equal 0, and then it has to change from positive to negative. So it changes from positive to negative.
Yep.
In terms of movement, not just like general mathematics.
Yep.
In terms of movement, it has to go through 0.
Exactly.
So
has to.
Through the intravenous value theorem, we can prove that it encapsulates them.
You're kind of right. It's not the intravenous value theorem. That would be like maybe a way that you would give blood. It may be the intermediate value theorem, right? And what the intermediate value theorem said, if you guys remember in unit 1, is that if I had a positive velocity and I had a negative velocity, then there has to be some value in the middle that reaches what? 0, right? So absolutely, okay? Absolutely. Are we good with that? All right, so what I want to do now is I want to find the total distance traveled, right? So I know that I want to figure it out from 0 to 3, but I also know that I changed direction, and that happened at what? Time 2, didn't it? How do I know it happened at time 2? Because that's when the what? Velocity was 0. Before 2, was it moving right? Yes. After 2, was it moving, actually I said it the wrong way. Before 2, it was moving left. After 2, it was moving right. So I had a positive to a negative velocity or a negative to a positive velocity. I hit 0, everything's there, so that had to have been a turning point. Cool? So where was I to begin? Well, to begin, I was at x of 0 was 3, and x of 3 was 0, right? All right, so these were where I began and where I ended. And where was I when I changed direction? Well, plug 2 in. And when I plug 2 in, what do I get? I get -1. So what happened? I moved left from 0 to 2. So I went from 3 to -1. So how far did I travel? 4 units, right? And then I changed direction at 2. And then I started moving to the right from 2 to infinity. But we only want to know what happens until 3, right? So for how far was it from 2 to 3? 1 unit. And so 4 plus 1 equals 5. We had a total distance of 5 units traveled. Okay. I actually kind of like doing something. I'm going to show you this here. You guys, I don't think ever did any parametrics, right? Was that you did do some parametrics? Okay. So if I did this as a parametric, what was that? Can somebody? Oh, I got it right here. T squared minus 4t plus 3. I'm going to put an arbitrary value of y in. Don't worry about this. And I want to do an experiment for 3 seconds, going from 0 to 3. Don't worry about what that t step means. Okay, what do you notice? I get a horizontal line, right? Okay, what I'm going to do is I'm going to trace this line. And I'm going to start at t equals 0. Okay, so here's my particle on a horizontal line, right? Where did it start? It started at a position of 3. Don't worry about this value right here, okay? This is arbitrary. The 1 is arbitrary. So at time equals 0, I started at 3. And what happened? Well, time started. And so the particle moved left. And it moved left, we said, for 2 seconds, right? Notice how it's slowing down. Why is it slowing down? Because it's preparing to stop. So here I am at 2 seconds at a position of -1. Now the particle starts to move right and speed up until it gets to that value of 0. So there it is, right? That's the actual motion of the particle, and we were able to describe it with some calculus. So far, so good? Wonderful. Next page. All right, so the only difference, guys, the only difference, Michael, from what we just did and what we're going to do now is instead of me giving you a function, I give you a graph. Okay? So this is a graph of a position function. So our entire conversation, guys, that we're going to have is identical to the conversation that we had on that last problem. So, on what interval, now notice what it says, open, right? Open interval. From 0 to 7, all right, well, this goes from 0 to 7, is the particle moving down? Well, guys, this is a position function. And notice, I didn't read it, I should have. Notice what it says here. It says the graph is a position function in inches of a particle moving on a vertical line. So yeah, if I can have a particle move on a horizontal line, then I can have one move on a vertical line, right? Sure enough. So what I have here is I have time that is progressing and position. So based on my picture, at what position was the particle to begin? 6, right? At time 0, the particle is at a position of 6. Well, notice something about this, guys. As time goes on, the particle is still at a position of 6, right? So what does that mean? For the first, how many seconds? 2 seconds, the particle didn't move, right? Then the particle started moving down, and it moved down for a time of how long? 2 seconds, from time 2 to time 4, right? And it moved from position 6 down to position -6, right? Then it raised itself up to position 0. That took 2 seconds. And then it went back down to position -3, and that took 1 second. Okay, so can we visualize what the particle's doing, right? Particle's staying, going down, going up, going down. Cool? All right. So on what open intervals is the particle moving down? Well, it starts moving down at 2, and it stops moving down at 4. All right, so 2 to 4. Yep. In fact, it's even nice enough to say what? On what open intervals, right? But then again, from where to where? 6 to 7, right? That word at the end, I know you just so badly want to just ignore it and be like, okay, I got the answer. Justify it. How do you justify it? Oh, thank you, Yates. That is exactly right. Right? Isn't that the values where there's a negative slope? And if there's a negative slope, then what does that mean about y values? They are moving down, right? So your justification is the slope of y of t is negative on these intervals. The slope of y of t is negative on these intervals, right? So negative slope, particle moves down. On what open intervals of time is the particle at rest? Okay, to be at rest, what did I say had to be true? I said that there had to be a slope of 0 in terms of the what? In terms of the velocity, right? So remember, at rest means velocity has to equal 0. Well, guys, is this a graph of velocity? No, this is a graph of position. Well, what is a graph of velocity? Well, the derivatives of this, right? So let me ask you this. What are all the values of this right here? They're all slopes of 0, right? Isn't it a slope of 0 from here to here? Is the particle at rest? Yeah, we said it's not moving, right? So from 0 to 2, I am at rest. And that's all. Now, I know that we're really anxious to say, well, Picardo, that's a turning point. Picardo, that's a turning point. But remember, are derivatives existing at sharp points? No, right? So this is not differentiable at 4. This is not differentiable at 6. Okay? So it is not at rest at those points, which is weird, isn't it? Michael, that kind of just screwed up everything you just said. Because you just said by the intermediate value theorem, if I went from a negative slope to a positive slope, I had to have hit 0, right? But remember, Michael, there was something about the intermediate value theorem that had to be true. The graph had to be continuous. And we're talking about the derivatives now, aren't we? So if I took derivatives of this, you would say they're all negative here, right? If you took derivatives of this, you would say they're all what? Positive. But if I asked you to take a derivative right here, you would say it does not exist. Got it? Okay, so it's kind of weird. It's kind of weird. And what would I say now? I would say on what intervals is the particle at rest? So we said 0 to 2. Justify the slope of y of t is 0 on this interval. All right. At what time does the particle change direction? At what time does the particle change direction? Well, we know the answer, but we don't like the answer, do we? Because what happened? The particle's sitting still, right? The particle's doing what? Going down. The particle's doing what? Going up. So did I change direction? Where? At 4, right? Okay, well, let's write that down. And where else again? And at 6? Ooh. What do we not like? We said that changing direction means what? Had to go from positive, negative, or negative to positive. And typically we're what? Have to have a particle that's where? At rest, correct? So let's go back for a minute. And what I want you to do is this. Between these two things, there are going to be some times when what? It's an and or, guys. Sometimes both have to be true. It all sort of depends on what we're accomplishing or what we're trying to do. And as the year goes on, we'll talk about those different scenarios. So here we saw something as a function, right? That function didn't have any sharp points. Do you guys agree the original function is just that of a what? It's a parabola, right? Does a parabola have sharp points? No, right? This one had a sharp point, right? So there are values that are not differentiable, right? So sometimes those arguments, we got to sort of use some common sense within them, okay? At what times does it change direction? So what are we going to say? In this case, we know we changed directions because what happened? We changed velocity signs, right? We went from a positive to a negative velocity, or vice versa. at t equals 4 and t equals 6. Cool? During the first 6 seconds, what is the displacement? Easy question, right? Displacement is where I ended up minus where I began, right? So it's going to be y of 6 minus y of 0. Where am I at y of 6? I'm at 0, right? And where was I to begin? I was at 6, so my displacement is negative 6, right? So I can say what? From t is an element of 0 to 6, the particle has moved. Don't forget about the example. Has moved what? Displacement's negative 6. Down. Yeah, because we're on a vertical line, right? The particle has moved down 6 units. And actually 6 what? Inches. But here's the thing, guys. Did it just go from here to here? No, it went from here to here and then what? Back up. So there was a change of direction, right? So even though it only moved down 6 inches, how far did it actually travel? Well, from here to here, it traveled how much? Nothing. From here to here, it have traveled how much? Well, from here, it traveled 6, then it traveled another 6, so 12. And then it traveled back up to here, another what? Another 6, right? So how much in all? 18 units? It says for the first what? 6 seconds, right? For the first 6 seconds, right? It didn't travel anywhere. It traveled down 12. It traveled up 6, so 18 total units. What is the velocity at 5? Uh-oh. How am I going to take a derivative if I don't have something to take a derivative of? I don't have a function. I don't have a function. Uh-oh. Well, I know to get a velocity at a specific time, I need a derivative. Right? Well, guys, isn't derivative just a really fancy way of saying a slope at a point? Okay, so check it out. Where am I at 5? At 5, I'm right here, right? Hey, guys, look at, isn't 5 on a straight line? And isn't the tangent of a straight line whatever the slope of the line is? So what's the slope of this line? Well, that's 6, 0, and that's 4, negative 6, right? So the slope of this line segment is 0 minus negative 6 over 6 minus 4. So the slope is 3. So guys, if the slope of this line is 3, then the tangent of this line also has a slope of 3. Guys, hey, if I asked you to create the equation of this line, could you figure it out by using the point slope formula? And do you agree that you would get a line that's y equals 3x, blah, 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 blah? Well, what's the derivative of that line that says y equals 3x, blah, 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 blah? 3, right? 3. So, yeah, the velocity at 5 is 3. And let's actually just do this. Let's just say that the velocity is equal to the change in y. Actually, I don't want to use y. I got to use what? What was the name of the function? Y. So the change in y of t over the change in t. Right? And that's because it's linear. Because it's linear. And I know somebody's thinking, what if it's not? Well, then you can't do it. Right? If it's not linear, then you can't do this. Okay. So what is my change? Oh, we already did it. It was what? 3, right? All right. So this is 2 inches per second, right? Wait, 3 inches per second. 3. Oh, this was over 2. Sorry, I flipped these. 2, 3. Okay, cool. Give me the velocity at 5.99999. Well, guys, look at this. At 5.99999, I'm still on this, aren't I? So what's the velocity at 5.9999? 3. All right. So velocity at equals 3. What is the velocity at 6? Oh, okay. The velocity at 6 is right here. Does the limit exist? No, because it's a what? Sharp point. And if you zoomed in on there, would you ever see local linearity? Never, right? So this does not exist. Okay, cool. We'll finish this up next week.